fantastic. Yeah, hello everyone. Yeah, nice. You guys are still alive. Amazing. Okay. Yeah, as Judy mentioned, my name is Morning, faculty in National University of Singapore. Uh, yeah. Gathering feedbacks. I was requested to give a half an hour quick lecture on convolutional neural network. I just want a quick understanding. How many of you already know what convolutional neural network is? Oh, so many. Am I doing? Okay. Nevertheless, if you already know, but okay, then maybe hopefully you offer some new understanding to you. For those who may be new to convolutional neural network, then do feel free to ask questions. Okay. And yeah, by the way, for my session, great thanks to just now for Frank and Professor Po Chin for the session. For my session, you don't need your laptop, and I'm also quite a jealous instructor, so I would like your attention 100% with me. So please close your laptop. Yeah, we will switch from laptop to a more advanced and reliable technology, which is your pen and paper. Yes, I hope everyone has a pen and paper. If you don't, yeah, okay, awesome, okay. Okay, let's keep going, okay? Okay. Yeah, just in case you may not know, I'll just reiterate why convolutional neural network is being a very popular type of deep neural network, particularly for medical imaging. Here's one of the story why it became popular. Rumor says, right? I don't quote me for that. A few years back, Google approached Professor Andrew Ng. I guess you may have heard, a very famous AI professor from Stanford. Of course, he left Stanford now, but he is a guest professor in NUS in Singapore. So anyway, so a number of years back, Google approached Professor Andrew Ng's lab, and please. I know him. Oh, you know him in person? I just saw so many videos and once he's starting from. Okay, fantastic. So don't tell him he's visiting us in our Singapore Daydon and being our opening speaker. So don't tell him that I spread rumors about him. Okay. Okay. Rumor says, yeah, Google approached his lab and say, oh, we have huge computes sitting there doing not much. That's before the large language model era. And can your lab do something cool about it? Of course, Prof. Andrew Ng said, yeah, of course. And then he asked his student to build something. So what his student built is that his student built quite a large convolutional neural network to watch YouTube for 2 weeks, right? And the task for the convolutional neural network is not really to predict anything to do classification, but more like unsupervised learning to find out patterns in all these YouTube videos that best summarize the YouTube. Right. So the setting is that the sort of the neural network or AI actually have no prior knowledge about human world. Its task is to watch YouTube for 2 weeks and try to find the patterns in our world, at least presented by YouTube. Okay. So of course, tons of computings and months of study. Then they build a neural network and they run. What came out which really impressed people is that in the early layers of neural network, of course, after optimizing all the loss functions and everything, right, that you just learned, the early layers of neural network is able to pick up simple shapes like down there. I think I have a more zoom in session. Yes, some simple shapes like lines, diagonal lines, circles, triangle. And in the deeper layers and the convolutional neural network, you start to find shapes that looks like human eyes, nose, mouth, etc. And even deeper, then you find layers that represent something looks like a human face. Right? If you look closely, you'll find out all these human faces are actually not a clear human face, but rather a blur one. Why that it will be a blur human face rather than a clear one? Any idea? Especially for someone who met Andrew Ng in person. Yeah, exactly. Because I would say that the AI's job is to find out patterns or templates that best represent kind of our world. So it wasn't meant to be anyone's face, but rather a almost an average of all the faces it is seen. Yeah, but it was impressive as I know that it was never mentioned to AI that there's such a thing as human or human face, right? It kind of pick it up or learn on its own. And besides human faces, what other things that you think the AI may pick up? Any other guesses? Pardon me? Yeah, part of the face. Of course, they pick up cars as well, and they also pick up something cute, right? I know it's a bit blur, as I mentioned, it is learned by the AI. It's supposed to represent a cat. And I know for a fact that within the audience, there's a cat lover that owns 2 cats, right? Although I don't know who that is, but at least one of you will be very connected to this. And also, very interestingly, the neural network also pick up something, right? Can you figure out what these things are? Dumbbells, right? Weights, right? And what's strange about these weights? Not really the motion. Yeah, it does attach to an arm, right? Or it touches the arm. Okay, why? Because, like I say, AI actually have no context of our world. They just watch 2 weeks of YouTube, right? And you probably don't see many YouTube videos have the weight just sitting there by itself. Most of the time, it will attach to quite a muscular arm trying to show off, right? And that's how AI understand that there's this shiny things always attached to a arm, right? AI, the neural network, we thought like this is actually one object in your human world, but we all know that it's actually 2 things in the world. That kind of also suggests that convolutional neural network kind of sees the world slightly different from human beings, right? We talk about loss function a lot. I don't think we think in the way of loss function, but that's how exactly AI learns slightly different from how we do. Okay, this afternoon, with half an hour, obviously we won't be able to build a convolutional network that can watch YouTube. Let's build something simple, right? And thanks to Brandon, who used to work in Meta to design this quite interesting exercise. So our task here is that let's together with pen and paper, right, build a simple convolutional network that can, looking at the images, just differentiate whether it's a cross or a circle, right? Simple enough for human being. It took us less than a second to learn, but let's see how it looks like for AI. And we make it realistic, right? So the cross and the circle don't have to be perfectly aligned in the center. You can rotate, you can in different scales and weights and etc. Okay, if you ask the machine or the AI to see, like, we can obviously quickly tell that both images are cross, but it's actually a non-trivial task for the machine, right? Because machine sees the images always as numbers, and if the machine will just do a very naive comparison of the 2 images, it may wrongly think that these 2 things are very different, because you can see that all the red crosses are these pixels that misalign among the 2. So we need something slightly more intelligent, okay? And then we observe that although the cross has rotated here, but some of the patterns, right, the imaging level patterns kind of remains there, okay? And these patterns include, you see the diagonal lines? I mean, yeah, in this direction, and the cross in the middle, and the other direction of the diagonal line, right? So no matter how you orientate the cross, whether it's aligned to the center or not, so these patterns kind of remains there. And that inspires the idea of the convolution network, because then using this mathematical concept called convolution filtering, we design an algorithm that teach AI to pick up these patterns like they are watching YouTube automatically. And why is it called convolution neural network? Because the most key component of the neural network, or you can imagine that the most sophisticated part of the brain of the AI perform this function called convolution filtering. And here comes the mathematics behind, right? Are you guys ready for mathematics in this hour of the afternoon? Cool, I'm just kidding, okay. I developed some animation to go through to help you understand. Okay, so when we perform convolution filtering, it's always reference to a filter or a pattern. But just now, if you still remember, I kind of tell you that we can identify a cross using 3 patterns, right? The diagonal line, the cross, and the other direction diagonal line. Let's just look at one of them, this diagonal line there, right? The small matrix. Does it work? Yes. So this guy, oops. Give me a second. Yeah. So this little guy here is the pattern or the filters that we are looking at. Okay. And this, the bigger guy, this is the original image, which is a a 9x9 original image. Okay, and when we perform a convolution filtering, we also perform it referencing to a targeting pixel. And in this case, this pixel in the circle is our target. Okay, I picked this pixel intentionally because it's the easiest example for this image. And the first step is that after you pick the pixel, using that pixel as the center, we will actually draw a 3x3 box around it. And why is it 3x3? Filter, yeah, thanks, Gabriel. So exactly, because the filter is 3x3, right? It's exactly to match the filter, okay? And once you draw the square, the box, 3x3 box, and then you do a pixel to pixel alignment, right? So for example, this left upper corner pixel will align to the left upper corner pixel in the filter. And then you do a multiplication between the two numbers. Okay, and of course 1 times 1 is 1. And here you have the first reading in your intermediate results in the filtering. Next, you move on to the next pixel. And in the original image, with -1, on the filter, we have -1 as well. And -1 times -1 is also 1. All right, I know this sounds very mathematical and I'm losing you. But can you also see what that means? Although it's a multiplication. Yes, Gabriel, yes. Yes, exactly, Gabriel. Thank you so much. Looks like you can do the lecture on my behalf. So yeah, I hope you can see that if the mathematics is too boring to you, what you can see is that if the pixels are the same, right, you will end up 1. If they're different, in this simple case, at least, you will end up with -1, right? But in theory, the same thing. We want to measure where are the matches and mismatches. And matches leads you to 1, mismatches is -1. Because, I mean, look back to the mathematics. If 1 times 1 is 1, -1 times -1 still 1, but once they're different, then they end up -1. Everybody okay? Okay, so this one, as I say, is a simple one because everything matches. But that's not the end yet, right? To finish the calculation, since we have 3x3, 9 pixels here, you basically just take an average, right? You sum up all the intermediate matching results and you divide by 9 and get an average value. In this case, it's exactly 1. And as Gabriel pointed out rightly, 1 means a perfect match, exactly in this case. Everybody following so far? Oh, good, okay. Now let's get to a more realistic example, right? Okay, the target pixel, I pick the right in the middle as the target pixel now. Okay, same thing, we draw a 3x3 square around it, and we do pixel to pixel matchings and do the multiplication. So first pixel still the same, and then we move on. Now it gets slightly more exciting, right? Because you can see that we do start to have pixels that don't look together. As I mentioned, if they're different, then you end up with -1. Speed up the animation a little bit, then yeah, if you do that all the pixel to pixel level, either multiplication or comparison, you quickly end up with this matrix. And to do that, right, as I mentioned, you need to do the averaging. So in this case, the end result, what's the average number? What's the end filter number? 7 to 9, you got tricked. Be careful, yeah, 5. Why is it 5 divided by 9, but not 7 divided by 9? Because you need to sum it up, right? Yeah, you shouldn't just count the matches. You must count the negative ones as well. Because the average is that you sum up everything in the 9 pixels, both the matches and mismatches, both of the ones and negative ones, and divide by 9. So it should be 5 divided by 9 here. And as Gabriel pointed out, that 1 gives you a perfect match, right? 0.55 kind of give you like 50% match. I guess you can probably guess -1 means what? Yeah, completely free, right? Complete mismatch. And that's the what convolution filtering does. And also, the computer does it systematically as well, right? Not just randomly, like I show you an example. It does systematically, and in this case, if we don't allow overflow, then the first center pixel you can do is here, right? I hope you can appreciate that because we need to draw a 3x3 circle. Okay, so you first calculate the sort of the filter value for this guy, drawing a 3x3 box, and it reference to a result here. And once it's done, you take a step from left to the right, and then now our target pixel is here. We do another filtering here, and we keep going that. So on this row, how many numbers we can calculate by doing that? 7, exactly. So we end up with 7. And once we finish this row, from left to right, what should we do next? Or what the machine will do next? Yes, it go to the next row, right? It moves to the next row. Same thing from left to right, very systematically. And so you end up with every row you have 7 numbers as the outcome, and you have 7 rows in total. Everyone following so far? Okay, because now it's your turn. You know your head. Okay, so we'll do a group exercise now, all right? So let's split from here, okay? So all of you gentlemen belongs to my right-hand side of your left-hand side. For the left-hand side, can I also divide from, Du Hao, can you raise your hand? Yes, so Du Hao and everyone underneath, you guys are, okay, so from that row onwards, you guys are group number 1. This is group number 2. At the back, you guys are group number 3 and group number 4. Okay, so as a team, okay, everyone do 1 row. Okay, on row, we have 7 rows. Forget about 5, 6, 7. Just focusing on 1, 2, 3, 4. Again, group number 1, group number 2, group number 3, group number 4. You just need to work out your row. Okay, so 2 and 4, you guys are lucky, right? I give you a head start. Okay, as a group, right? Gather together, use pen and paper, calculate the value for that row. Okay, and it's not free labor. The winner, the first team get the right answer. You want to do it fast and accurate. Okay, once you finish, you feel like, oh, we done it. You let me know, but you have only 1 chance. The first team got it correct for your row. There's a special prize for you, I promise. Okay, get to your team. Yes? Something like that, yes. Get to a group, get paper and pen. Give me 1 second. So to discuss the team, each team only have 1 chance. So make sure you get the acknowledgement for your teammate, because if you're wrong, your chance is gone. No, you take the 4th row, right? So for team 4, I'm not tall enough. Okay, team 4, you'll be looking at the 0.55 row. Yes, you guys have a head start, right? Team 4, you'll be looking at the 0.55 row. Yeah, so team 3, you'll be the row above it. Right, 2, okay, should be easier. Yeah, go by rows. You guys are the second row in the result, right? Not in the original image. You guys are the first row in the result, not the original image. Yes. Okay.
So right here, why is this one right here? This position right here.
Yes. Because you have. How many misses you have? This guy, you look carefully, right? At least, okay, the middle
Because I'm
line.
missing. Because I'm missing. Okay, so it's matching on the black, but it misses all the whites.
So 2-1.
No, it matches 9 by 9. Right? It matches every single pixel, right? So yeah, it misses all these three. It misses these two as well, but this corner is correct. This three corner is correct. Okay.
Let's do one together.
We did a bigger
so it's
paper.
matching here, or it's not matching.
2-1.
It matches here because it matches black to black. It
Yes.
matches here because it
Black
matches
to, yeah, black to black, yeah.
But these are black when they're supposed to be white, and these are white when
Yes,
they're supposed to be black.
yes.
Okay, now I understand.
Okay, cool.
Okay. All right.
Oh, awesome.
No, I'm not even doing the math. I'm just writing.
Oh, he's just writing that.
Right. So this is 2-1, right? We have a 1 and a 1. Sorry. Did I do it right? Yeah.
So it's my. You're starting here, right? Are you starting this one?
Yeah, the middle one is a minus 1.
Sorry. Yeah, it's, yeah, I noticed that it's
And everything else. So we only have 2 ones. Right? Alright. So now, if we do minus, we're going to take top left on there, 1 times a minus 1. So our result is minus 1. Then we take 1 times minus 1, so minus 1. Then we take minus 1 times minus 1, that's a 1. We take minus 1 times minus 1, that's a 1. We take minus 1 times 1, minus 1. 1 times minus 1 is minus 1. Minus 1 times minus 1 is 1. Minus 1 times minus 1 is 1. And 1 times minus 1 is 1. So we have 1, 2, 3, 4 minus 1. So our total is negative 1 for 2-1. I got minus 1.
But he's done. He's already done. No, he's done 2-2.
No, we have 2-1. Like a picture of this to draw.
Should have printed this one. We should first do context, right? The one he's done. No, he's done the second one. He's done the first one. But he's done for us 2-2. That's the next one.
I did 2-1. I didn't do 2-1?
No, you did 2-1.
Oh.
But we should try the 2-2.
2-2 is already done. So let's do 2-3.
So 2. Okay, so what did you get the answer?
Minus 1.
Minus 1. And then 2-2 is 1.
2-2 is 1. So I'm going to try and draw this properly.
Was it minus 1 divided by 9?
Yes. Good point. So this would be our box for 2-3.
Chance.
Yeah.
You sure? You only have one chance.
That's cheating, man.
Sorry for that.
He's already done it?
He's done it in Excel.
Yeah, I can't tell you. I mean, once I check, means if you're wrong, you're out.
Dash 3-7.
Yes.
So we multiply this box by that top left.
Okay, you guys are team number 1. Okay, team number 1. Okay,
We're just on 2.
But we can do it. So let's do 2-3.
okay,
It'll be
okay. I got it. But I won't share you the rest first. Okay.
1.
Yes. You guys. No, but you guys took. The first team took 4 minutes. All right. The rest keep going.
Oh my goodness, we already lost.
Minus 1.
No, I only released to the end. Yeah.
So we only
Yes.
have.
Yes. Yeah.
We've actually no correct answers. Oh no, that's not true. Sorry.
Yeah.
The 2 that are correct. 1, 2. So you just count correct. 1, 2, 3.
Should be left, middle, and bottom.
4 minus 5. So minus 1
So
over 9.
minus 1 again. Did you get minus 1 over 9 for 2-3?
Yeah.
Okay. Good. Now we're gonna go to.
The Excel makes it make a little bit.
There we go. The next one. So how many correct? That's correct. That's correct. That's correct. That's correct. That's correct. So 5 correct.
5 correct.
Yep. For the rest, yeah, team number 1 already submitted in 4 minutes time. but you still have a chance because I haven't told them whether they're correct yet. If they're wrong, then they're out, right? So keep going.
But it makes so much sense when you have it written out in that cube instead of trying to imagine it.
Do 1 minus 1 over 9. Four, right?
Four correct.
So minus 1.
So it's not even putting a minus one.
So Amy, you guys got it?
Yes.
Almost there. Okay. Good. Good. Good.
Two correct, three correct, four
Okay.
correct,
Go for it.
five
Yeah.
correct. So 1 out of 9.
Okay. No worries.
And last one. One correct, two correct, four correct. So -1 over 9. So that should be pretty easy.
Did you get those? Minus.
1 minus 1
0. That's it to 0.
That's not.
This was the first one. Minus 1 over 9.
Should have been 5.
Did you count them?
I
Did
did
you
something
subtract out? You didn't subtract
Yeah,
out
I
the
did.
misses. I think we have 0, right? Because there's one, two, three, four negatives. 1, 2, 3, 4. No, wait. Sorry. How many positives? 1, 2, 3. So -1 over 9 is our answer. Two.
Morning. You got it?
-1 9. 1 9.
No. Okay.
-1 over 9.
Is that okay?
1, 2, 3, 4, 5, 6, 7.
You guys are team number 2, right? Okay, let me check. I can't tell you yet. Yeah.
Huh?
I can't tell you. Okay. Yeah. No. Just one chance. That. Okay. Okay. Congratulations to Group 2. They managed to submit their answer. No worries, Team 1. In 7 minutes. All right. Just for record. Team 3 and 4. Keep it going.
Yes, it was 9 over 9.
Oh,
'Cause
9
they were-
over 9.
Yeah,
They got a
because
1.
number
Yeah.
2 was all of them was correct.
Yeah, and it makes sense because if you go across row 2 for us, none except for that cell 2-2, nothing else matches.
So Team 2 and 4 are in the interest of time.
So like
Sorry that I give you 2 more minutes. All right. So we stop at the 10 minutes mark.
we're in this row, right? The only one that matches is this.
Yep.
All of these match very, very poorly.
Yes.
So it makes sense we have super low scores. When there is a match, it matched 1 out of 9. And then at most, we got a negative score. So unless we did the math wrong, but I think we're pretty close.
So how come the other one is not a match and it's also wrong?
Well, because
Got it?
the 3 box is the same as that box.
Oh, I
That's
Okay.
why it's a full
8
match.
minutes
see.
mark.
Opposite. I see. Okay.
Yeah, good 4. Okay.
Fourth row.
4 row. Okay.
You know?
Okay.
No, you're multiplying with that. But then you're adding it.
Okay. I can actually tell you that you are correct.
So
Do you understand? Like
You are correct, but you are team number 3. So okay, it all depends on whether they are correct. Okay. I will tell you now that you are correct. Okay. Congratulations. Group 4 actually got the answer correct after 8 minutes mark. Okay. Well done. Well done.
if it's a
Not yet. Not yet. Not yet. Not yet. Not yet. Not yet. Chill. 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 Not yet. Not yet.
cell in the filter.
Okay, so
In
it
the
has to be
filter.
exactly
Yeah. Yes, that's life. That's yeah. That's my enjoyment. You know? You don't take that away from
Left
it.
there is a 1. So that's you multiply that and you get a -1. The next box we have a 1. That is a -1. Okay. So you go through and the only cells that we have that match are this cell matches the top right.
if you go to the next one, which this is -1.
This one matches the middle left.
Yes. So then
That doesn't match. Then these two match, right? So how many matches did we get? We got
-1,
1, 2, 3, 4. So each of those those would be positive 1, right? Because it'd be a -1 times a -1. The other ones are
Got it.
-1. So you have
So you multiply by -1.
no, if they match. So like this cell is a -1, but times a -1. So it's a positive 1. So you get a 1. So all the matches, whether it's a 1 times a 1 or a -1 times a -1, you get 1, right? So anytime they match, you get +1. Anytime they don't match, you get -1. So in that cell, we have 4 matches. So we're at +4. We had 5 mismatches. So we're at -5. So our total score for this box is -1. Then all you do is you go to the next box and you do it again. This one is a perfect match, right? So this one is 1 plus 1 plus 1. So this you get 9. So you 9 divided by 9 is 1, right? Then you go to the next cell. So the next cell is and so on, right?
But you get the idea.
So this one we have 1 match, 2 match, 3 match, 4 match. So 4 correct,
So,
5 incorrect.
yep. Okay.
-5.
Yeah. So yeah. Sorry, guys. I'm glad that everyone's having a good time. Having a good time. Okay. Yeah. Can everyone get a seat? Yes. Almost done. Okay. So okay. So now it's interesting. So I already told that team number 4 they got it correct. And the second one on a 6-minute mark, group 2 submitted the result. But unfortunately, you guys missed 1 number. So now it's all either group, team 1 or team 2, right? Do you think they got it correct in 4-minute mark? Yeah, they did. Okay, and as promised, there's a prize, right? Which is a hug for me. No, I'm just kidding. No, it's something slightly better. Okay, as the organizer for Singapore Daydon, I will waive the registration fee, which worth $200 for our Singapore Daydon for all of you. I know why, because Singapore venues are expensive, food are expensive, but then our food is good, right? And it'll be fun, okay? So I invite all of you to Singapore, and if you come to Singapore, I'll definitely waive the registration fee for all of you, and thanks for participating. Okay. Okay. And I'm glad that yeah. Okay. So yeah, I mean yeah, you did that. Okay. So so okay. So don't mind the numbers, right? I mean this is I mean I will share the slides so you don't have to copy down anything. Okay. What's the observation? Where are the big numbers? Where are the huge numbers, like close to 1? Where are the yeah, exactly. The one kind of the middle where the matches, right? Because that's how kind of convolution neural network AI kind of sees images. That they basically find where the matches, and obviously you can see that on the other diagonal direction, either there are very small numbers or negative number, because that's where the mismatches are. And no offense to all the human beings in the room, our fastest team took about 4 minutes. And guess if we throw this into a NVIDIA GPU, how long it may take? 1 minute? Yeah, it's too small to measure. It's definitely less than microsecond. Because this is too simple for it. So it actually didn't measure its potential, right? You can compute much bigger matrix in microseconds. This is way too easy for it. So not to put us down, just to mention that we actually see the world and understand the world very differently. Maybe that may suggest how we may work together in future. And as I mentioned early on, so we use the clause as a symbol for convolution filtering. So as I mentioned earlier, we have 3 different patterns. So we actually compute that 3 times, right? But for GPUs, we have to compute 3 times. But for GPUs, they actually process all this in parallel, right? Because within 1 millisecond or even less than that, all is out, right? So yeah. So for the other 2, get your paper and pen again, and let's do it one more time. I'm just kidding. Yeah, no, I don't want to torture you anymore. And very importantly, because I told you that to recognize a clause, we have 3 patterns here, right? But in real life, who designed these patterns? In real life, do you think the humans? Because just now, I believe Feng or Pochen mentioned that in real life, how many filters are there in a common convolutional network nowadays? Millions. So do you think human beings, we can set all these filters, millions of them, one by one? No. The beautiful thing about this is all learned automatically by AI. Based on what? We talk about that. What function? Convolution and what convolution and based on what function? That Feng and Pochen have been talking about it for. Pardon me? Based on, yes, same thing, to minimize the loss function. Because here our task is to recognize or differentiate a clause from circle. So all these filters, in the beginning, usually we may start them as a random number. Okay? And because there's a loss function, we feed the AI probably thousands of images of clause and circle and give them the right answer so they can minimize the error. And over, again, funny terms, right? Epochs. Over many epochs, right? And many iterations within the epoch, the AI slowly learned that maybe the perfect patterns to differentiate clause and circles are these three, right? So slowly. And then, but the humans, we are not entirely useless, right? So what, as a humans, what do we have to design here? What things have to be decided by us? Yes. Yes, exactly the dimensions of the filter, right? Because here we put 3 by 3, we have 5 by 5, 7 by 7, 9 by 9. You notice why is it always in odd number? Yeah, because we need a center point, right? Because 4 by 4, like, we can't find a center. So it's always in an odd number. And the common ones are 3 by 3 and 5 by 5. And why? Pardon me? Have that at the center. Must be an odd number. But odd number, we can have 3 by 3, 5 by 5, 7 by 7, 9 by 9. But in practice, the most popular one now are 3 by 3 and 5 by 5. Yes.
So with a 3 by 3 square, you lose one edge width around the edge.
Yes.
5 by 5 square, you lose 2 edge widths around the edge.
Yes.
Right?
Yeah.
And the 7 by 7, you lose 3 edge widths. So you have to spend more of the image in order to estimate what's going on with the larger the rectangle, but the larger the square is.
Yes, please.
I think it should be 5 by 5 to reduce the number of computations.
So, yeah, because the bigger the filter, you kind of have slightly better global views because your filter is bigger. The smaller ones, you're focusing more on the details, right? So you kind of find a balance. There's some heuristic there. But the true answer, yes, please. Yes. But the true answer is that mainly is try and error. Okay? Yes. So you have to learn this in AI scientists. Although we call ourselves AI scientists, but a lot of things is not so much science. It's really that we try out all these configurations. At the end of the day, we realize we try everything, and 3 by 3 and 5 by 5 are kind of the most highest performance, right? Then we have some heuristic, exactly like you presented, could be these two are balanced between localization and globalization, but then there's no theory proving behind. But yeah, and we need to decide the size of the filter. Besides the size of the filter, what other things as a human designer we need to decide? The number of filters as well, right? Because here we have 3. Like I say, in real life, we have thousands or 10,000s or millions. Okay, in real life, usually a layer either we have 1,024, 2,056, and so on and so forth, right? It's always in the power of 2. Why?
Because before 0 or 1, we don't have more.
Yeah, it's related to the computer. The reason being is we have to assume or accept the fact that when the neural network gets into millions of filters, it will be so big that it can't fit into one single GPU. We have to distribute parallelization, Gabriel was talking about. We have to distribute the compute into more than one GPUs, right? You can imagine when you have odd numbers, like if you have 3 filters in this case, actually it's a very bad design. Because now, assuming I have 2 GPU, right? Then you can put the first filter on my left-hand GPU, the last filter to my right-hand GPU. Then the middle one, where does it go? you have to first develop a logic to assign to one of them, and then the other two have to wait for the third one to compute. So it's very inefficient. And since there are millions of such filters, we want everything to be most efficient. So it's the number of filters is always in the power 2, so it allows us to keep splitting when we have more and more GPUs. And when we add GPUs, usually we also add GPUs in the order of on the power 2 as well. So that's why when we scale up our data dawn, Harry is going to face a much bigger bill that grows exponentially when we spin up more and more GPUs. Okay, so that's the, in the just time, I'll quickly go through, right? So we have, besides the convolution layer, which is the most important layer, we have other layers as well that I won't have time to cover. But then after that, the fun part comes in is that we're basically playing Legos, right? We just stack all these layers together and build a very deep, that's why I call it deep neural networks, that serve the purpose. And how do we design these Legos? How do we know that which Lego arrangement is the best? What's the best thing AI scientists? Exactly, we try and error, right? We still keep trying. And as far as someone as generous as Harry and Judy paying for the GPU, eventually we'll find one. So I definitely eat into Harry's time too much. And that's the end of a quick introduction. You can find it full tutorials on Brandon's YouTube channel. And if you have any questions, feel free to grab me later on. Send me an email. Send to Slack. Happy to share more with you later on. And Team 1, hope to see all of you in Singapore. Thank you, guys.